This is SpaceTime, Series 24, Episode 78. Coming up on SpaceTime, looking back at the cosmic dawn. The Hubble Space Telescope still offline as technicians struggle to fix it. And planet Earth reaches aphelion. All that and more coming up on SpaceTime. A new study claims the first stars began shining between 250 and 350 million years after the Big Bang 13.82 billion years ago. The findings, reported in the monthly notices of the Royal Astronomical Society, are based on a study of 6 of the most distant galaxies currently known, galaxies whose light has taken almost the entire existence of the universe to reach here. The authors found that the distance of these galaxies away from Earth corresponded to a look-back time of more than 13 billion years, an era when the universe was only 550 million years old. Analysing images from the Hubble and Spitzer space telescopes, the authors were able to calculate the age of each of these galaxies as ranging from somewhere around 200 to 300 million years, and that allowed them to estimate when they first formed stars. The birth of the first ever stars, known as cosmic dawn, was a key event in the evolution of the universe. See, it marked the end of the cosmic dark ages, the time before the first stars shone. And the ultraviolet light from those very first stars triggered the beginning of cosmic reionization, the process that would eventually make the universe transparent and look the way it does today. To determine the age of cosmic dawn, the authors analysed starlight from the galaxies as recorded by the Hubble and Spitzer space telescopes. They were looking for a marker in their spectrum, which is indicative of the presence of atomic hydrogen in their stellar atmospheres. This provided an estimate of the age of the stars. See, the hydrogen signature increases in strength as the stellar population ages, but then it diminishes again when galaxies are older than around 1 billion years. That age dependence arises because the more massive population 3 stars which contribute to this signal burn through their nuclear fuel fairly rapidly and therefore are the first to die. One of the study's authors, Roman Meyer from University College London and the Max Planck Institute in Heidelberg, says the same age indicator is used to date stars in our own stellar neighbourhood in the Milky Way, and it can just as easily be used to date extremely remote galaxies in the very early universe. Using this indicator, astronomers could infer that the 6 galaxies hosting these stars must have already been between 200 and 300 million years old. In analysing the data from Hubble and Spitzer, the authors needed to estimate the redshift of each galaxy, which indicates their cosmological distance and hence the look-back time at which they were being observed. Redshift is a signature of how much the universe has expanded since the Big Bang. To achieve this, Meyer and colleagues undertook spectroscopic measurements using a full armoury of powerful ground-based telescopes. These included ALMA, the Atacama Large Millimetre Submillimetre Array Radio Telescope, the VLT or Very Large Telescope Array, the twin Keck telescopes in Hawaii, and the Gemini South Telescope. Combining these measurements allowed the team to confirm that looking at these galaxies corresponded to looking back in time to when the universe was just 550 million years old. Over the past decade, astronomers have been able to push back the frontiers of what they can observe to a time when the universe was just 4% of its present age. However, due to the limits of transparency in Earth's atmosphere and the capabilities of the Hubble and Spitzer space telescopes, astronomers have now pretty well reached the limit of their abilities, at least with the present technology. However, all that should change with the launch in November of NASA's new Hubble replacement, the James Webb Space Telescope. The authors believe James Webb will have the capability to directly witness the cosmic dawn and the birth of the very first stars between 250 and 350 million years after the very beginning of the universe. This is SpaceTime. Still to come, the Hubble Space Telescope still offline as technicians struggle to fix it, and the latest OneWeb launch adds to the growing Starlink satellite pollution problem. All that and more coming up on SpaceTime. NASA's Hubble Space Telescope remains offline following a major onboard computer crash last month. The issue stopped all scientific observations aboard the orbiting observatory, and all attempts to identify and rectify the problem so far have failed. NASA mission managers are now preparing for procedures to turn on backup hardware. Engineers are continuing to focus their efforts on the telescope's payload computer, which they think could be the issue behind the June 13th failure. The telescope is equipped with two payload computer systems, one of which serves as a backup. Both are located on the Science Instrument and Command and Data Handling Unit. The systems coordinate and control science instruments, bridge communications, pass signals, and store operational command memories. In parallel with the investigation, NASA is preparing to test procedures on the ground to turn on backup hardware on board the spacecraft. For now, the telescope itself and its science instruments remain healthy and in a safe configuration. With the source of the computer problem lying in the Science Instrument Command and Data Handling Unit where the payload computer resides, several systems on the unit could be the culprits. Technicians are currently scrutinizing the Command Unit's Science Data Formatter, which sends and formats commands and data. They're also looking at a power regulator within the Power Control Unit, which is designed to ensure a steady voltage supply to the payload computer's hardware. Now, if one of these systems is determined to be the likely cause, mission managers will need to undertake a complicated operational procedure to switch to the backup units. And this procedure will be more complex and riskier than last week's attempts, which involved switching to a backup payload computer and memory modules. To switch to the backup command unit, science data formatter or power regulator, several other hardware boxes on the spacecraft would also need to be switched because of the way they're all connected to the Science Instrument Command and Data Handling Unit. So over the next week, engineers are reviewing and updating all the operations, procedures, commands and other related items needed to perform the switch to the backup hardware. They'll then test their execution against a high-fidelity simulator here on Earth. And only if that practice run works will they try it with the real thing in orbit. Mind you, it's not the first time this has happened. The team performed a similar switch back in 2008, which allowed Hubble to continue normal science operations after a command unit and science data formatter module failed back then. The fifth and final Hubble servicing mission aboard the Space Shuttle Atlantis on STS-125 back in 2009 then replaced the entire Science Instrument Command and Data Handling Unit, including the faulty Command Unit and Science Data Formatter module, with the unit currently in use. And since that mission, Hubble has taken more than 600,000 additional observations to exceed 1.5 million during its lifetime. Hubble's work has continued to change science's understanding of the universe and mankind's place in it. Launched in 1990 aboard the Space Shuttle Discovery on STS-31, the Hubble Space Telescope has been observing the universe for over 31 years from a 541-kilometre high geocentric low Earth orbit. The telescope's actually based on keyhole spy satellites operated by the National Reconnaissance Office, but it's specially fitted out and positioned so that instead of looking down to Earth, it looks up into the cosmos. By avoiding distortions in Earth's atmosphere, Hubble's 2.4-metre telescope has an unobstructed view of the universe, seeing stars and galaxies, some more than 13.4 billion light-years away. The 11,110 kilogram Space Observatory has contributed to some of the most significant discoveries in human history, including the accelerating expansion of the universe, the evolution of galaxies over time, and the first atmospheric studies of planets beyond our solar system. This is SpaceTime. Still to come, OneWeb adds to the growing problem of Starlink satellite pollution, and we'll check out the July night skies on Skywatch. All that and more still to come on SpaceTime. Roscosmos has successfully placed 36 British OneWeb Internet broadband telecommunications satellites into orbit. The Soyuz 21B rocket, equipped with a frigate upper stage, was launched from the Vostochny Cosmodrome in Russia's Far East. The mission is the latest in an ongoing campaign by OneWeb to develop a constellation of an initial 650 satellites by the end of next year. The 150 kilogram spacecraft, being placed in 450 kilometre high orbits, will provide 3G, LTE, 5G and Wi-Fi coverage. In order for OneWeb to achieve its initial ambitions, 16 Soyuz launches have been slated between December 2020 and the end of 2022, each launching 36 satellites. The latest launch brings OneWeb's constellation up to 254 satellites, with previous launches in March, April and May this year alone. OneWeb is competing directly with SpaceX's Starlink project to develop massive satellite constellations containing thousands of spacecraft, providing blanket broadband coverage across the planet. The problem is so many satellites are intrusive, leaving bright star trails across the sky. They not only look bad, but worse still, they cause serious problems for astronomers trying to undertake important scientific research. And near misses between spacecraft have already occurred. Undoubtedly, things will get a lot worse when there are thousands of these spacecraft up there. This is SpaceTime. And time now to turn our eyes to the skies and check out the celestial sphere for July on Skywatch. July is the 7th month of the year in both the Julian and Gregorian calendars, and is named after the Roman Emperor Julius Caesar, who was born during the month. Before being called July, the month was called Quintilis, which is Latin for fifth. The addition of the months January and February brought an end to that. On average, July is the coldest month in the year in the southern hemisphere, which is experiencing winter, and also marks the time when Earth is at aphelion, its furthest orbital position from the Sun. Of course, temperatures, or more accurately seasons on Earth, aren't dictated by the distance from the Sun, but rather the length of a day, and hence the amount of sunlight a given part of the Earth receives, which is governed by the tilt of Earth's axis. Consequently, that's why July is on average the warmest month in the northern hemisphere, which is currently experiencing summer. During this year's aphelion, the centre of the Earth will be 152,100,527 kilometres from the Sun. That's around 5 million kilometres further away from the Sun than during perihelion, when the Earth will be just 147.1 million kilometres away from the Sun. This year's aphelion occurred at 8:27 in the morning of Tuesday, July the 6th, Australian Eastern Standard Time. That's 6:27 in the evening, Monday, July the 5th, US Eastern Daylight Time, and 10:27 p.m. on July the 5th, Greenwich Mean Time. Over cosmic time, these dates change. That's due to variations in Earth's orbit, such as eccentricity, as well as axial tilt and precession, which all follow regular cyclic patterns known as Milankovitch cycles. Eccentricity involves changes in how elliptical Earth's orbit is around the Sun. None of the planets actually orbit the Sun in perfect circles, although Venus and Neptune are the closest. Instead, they all have elongated orbits which vary over time. As well as that, Earth spins on an axis which is currently tilted at 23.4 degrees compared to the ecliptic, Earth's orbital plane around the Sun. But this angle of tilt also changes over time, influenced by, among other things, the distribution of the Earth's mass. And just like a spinning top, the rotational axis of the Earth also changes its orientation through a process called precession, changing its position in relation to fixed background stars over a 26,000-year cycle. Now, all these effects impact the amount of solar radiation reaching the Earth, what time it reaches the Earth, and consequently, the planet's seasonal and climatic patterns. Right now, the Southern Cross is at its highest point in the southern sky, and is pointing directly towards the southern celestial pole. The Southern Cross falls within the constellation Centaurus the Centaur, the half-human, half-horse of Greek mythology, and the creature is holding a bow loaded with an arrow. The Centaur's front legs are marked by the two pointer stars Alpha and Beta Centaurus. At 4.3 light-years, Alpha Centauri is the second of the two pointer stars from the Southern Cross and is also the nearest star system to the Sun. The Centaur's back arches over the Southern Cross, and just above this is Omega Centauri, a spectacular globular cluster, visible with the unaided eye from dark locations. Globular clusters are tightly packed spheres containing thousands to millions of stars. They're thought to have all originally been born at the same time from the same molecular gas and dust cloud, or they're the cause of small galaxies which have been consumed by bigger galaxies through galactic cannibalism. Omega Centauri is about 16,000 light-years away. A light-year is about 10 trillion kilometres, the distance a photon can travel in a year at 300,000 kilometres per second, the speed of light in a vacuum, and the ultimate speed limit of the universe. Omega Centauri is one of the largest and brightest of the 150 or so globular clusters known to orbit around our Milky Way galaxy. Centaurus was one of the 48 constellations listed by the 2nd century astronomer Ptolemy, and it remains one of the 88 modern-day constellations. Turning to the right or west, and you'll see the constellation Leo the Lion, just above the western horizon. Its brightest star is Regulus, or the Little King, located about 79 light-years away. Regulus, designated Alpha Leonis, is actually a 5-star system, organised into 2 pairs. Regulus A is a spectroscopic binary, comprising a spectral type B blue-white main sequence star, some 4 times the mass and 288 times the luminosity of the Sun, and a faint companion star thought to be a white dwarf, the stellar corpse of a Sun-like star. Spectroscopic binaries are stars that can't be resolved by optical telescopes into 2 separate objects, and can only be separated by observing their individual spectroscopic Doppler shifts as they orbit each other. Astronomers describe stars in terms of spectral types, a classification system based on temperature and characteristics. The hottest, most massive and most luminous stars are known as spectral type O blue stars. They're followed by spectral type B blue-white stars, then spectral type A white stars, spectral type F whitish-yellow stars, spectral type G yellow stars, that's where our Sun fits in, spectral type K orange stars, and the coolest and least massive known stars are spectral type M red dwarf stars. Each spectral classification is also subdivided using a numeric digit to represent temperature, with 0 being the hottest and 9 the coolest, and a Roman numeral to represent luminosity. So put all that together, and our Sun is a spectral type G2V or G25 yellow dwarf star. Also included in the stellar classification system are spectral types L, T and Y, which are assigned to failed stars known as brown dwarfs, some of which were actually born as spectral type M red dwarf stars, but became brown dwarfs after losing some of their mass. Brown dwarfs fit into a category between the largest planets, which can be about 13 times the mass of Jupiter, and the smallest spectral type M red dwarf stars, which can be 75 to 80 times the mass of Jupiter, or 0.08 solar masses. Located further away are Regulus B, C and D, which are dim main sequence stars. At the opposite end of the constellation from Regulus is the star Beta Leonis, or Denebola, the horse's tail. It's also a luminous blue-white star, about half as bright as Regulus, and the 3rd brightest star in the constellation Leo. Beta Leonis has about 1.8 times the Sun's mass and about 15 times the Sun's luminosity. It's suspected of being a dwarf Cepheid or Delta Scuti type variable star, meaning its luminosity varies slightly over a period of several hours due to pulsations on its surface. Algebra or Gamma Leonis is a binary system with a visible 3rd component. The 2 primary stars are located about 126 light-years away and can be resolved in small backyard telescopes. Both are yellow giants orbiting each other every 600 Earth days. The unrelated tertiary star named 40 Leonis is a yellow tin star that can be seen through binoculars. The star's traditional name Algebra means forehead. Delta Leonis or Zosma is a blue-white star 58 light-years from Earth. Epsilon Leonis is a yellow giant some 251 light-years from Earth. And Zeta Leonis is an optical triple star. The brightest component is a white giant about 260 light-years from Earth, while the second brightest star, 39 Leonis, is widely spaced and located to the south of the primary. The 3rd and faintest star in the system, 35 Leonis, is to the north. Lota Leonis is a binary star system visible in medium-sized backyard telescopes. Located some 79 light-years away, Lota Leonis appears to be a yellow tin star with 2 components orbiting each other every 183 Earth years. Finally in Leo, let's look at Tau Leonis. Visible as a double star through binoculars, it includes a yellow giant located some 621 light-years from Earth, and binary secondary star 54 Leonis, which is actually a pair of blue-white stars. They're visible in small telescopes and located some 289 light-years away. The constellation Leo also contains many galaxies, including the spiral galaxy Messier 66, as well as Messier 65 and NGC 3628, which are known as the Leo triplet. Located some 37 million light-years away, the Leo triplet has a somewhat distorted shape due to gravitational interactions between Messier 66 and the other two galaxies, which are cannibalizing stars from Messier 66. Eventually, the outermost stars may well form a dwarf galaxy orbiting M66. Both M65 and M66 are visible in large binoculars or small backyard telescopes, but their concentrated nuclei and elongation are only visible in larger instruments. Other bright, well-known deep sky galaxies in Leo include Messier 95, Messier 96, and Messier 105. Messier 95 and Messier 96 are both spiral galaxies, each about 20 million light-years from Earth. Both look like fuzzy objects in small telescopes, but display their spectacular structures in larger instruments. M95 is a barred spiral. Another barred spiral, NGC 2903, is thought to be similar in size and structure to our own Milky Way galaxy. It was discovered by William Herschel in 1784. Close to the M95-M96 pair is the elliptical galaxy M105, which is also about 20 million light-years away. The constellation also contains the Leo Ring, a cloud of hydrogen and helium gas orbiting two of the galaxies in the constellation. A gravitationally lensed object known as the cosmic horseshoe is also found in Leo. Above Leo, you'll find the constellation Virgo, the Greek and Roman goddess of wheat and agriculture. Virgo's brightest star, Spica, is visible above the western horizon. It's located some 250 light-years away. Spica is Latin for ear of wheat, which Virgo is holding in a hand. Spica, or Alpha Virginis, is the 16th brightest star in the night sky, and is both a spectroscopic binary and a rotating ellipsoidal variable, a close binary system whose stars are not eclipsing but cause apparent fluctuations in brightness because of changes in the amount of light emitting area visible to the observer. Spica's two main stars orbit each other once every 4 Earth days and are so close they're egg-shaped rather than spherical and can only be separated by their spectra. The primary is the blue giant variable Beta Cepheid star. It undergoes small rapid variations in brightness. These are caused by pulsations of the star's surface, thought to be caused by the unusual properties of iron at temperatures of 200,000 degrees in the stellar interior. It has about 10 times the Sun's mass and about 7 times its diameter. The secondary star in Spica is smaller than the primary, but it's still some 7 times more massive than the Sun and has 3.6 times the Sun's diameter. Turning to the north now, and the constellation Boötes, the herdsman or ploughman. There you'll see the bright orange-red star Arcturus, or Alpha Boötes, just above the northern horizon. It's a red giant located just 36 light-years away, a bloated, aging star some 7.1 billion years old, nearing the end of its life. Although not much more massive than the Sun, it's now expanded out to some 25 times the Sun's diameter and will soon puff off its outer gaseous envelope as a planetary nebula, revealing its white-hot stellar core, a white dwarf, which will then slowly cool over the eons of time. Another bright reddish-looking star, this time in the east, is the red supergiant Antares, meaning the rival of Mars, because of its appearance and location in the sky, which appears to be opposite of Mars in the sky. Antares is one of the biggest known stars in the universe. It's enormous, 18 times the Sun's mass, 10,000 times its luminosity, and 883 times the Sun's radius. As we mentioned in last month's Skywatch, were it placed at the centre of our solar system, its surface would extend out close to the orbit of Jupiter. Despite being some 550 light-years away, Antares is still the 15th brightest star in the night sky. Unlike the Sun or Arcturus, the death of Antares will be far more spectacular. Antares is destined to explode as a core collapse or Type II supernova. When it does so, sometime in the next few 100,000 years, it'll appear as bright in the Earth's sky as the full moon and be quite visible even in daytime. Antares has a companion star, Antares B, a spectral-type blue-white main sequence star more than 7 times the Sun's mass and 5 times its diameter. Antares is the heart of the Scorpion in the constellation Scorpius. Below Scorpius is the constellation Sagittarius, the Archer, which points the way to the centre of the Milky Way galaxy. Sagittarius is commonly represented as a winged centaur, pulling back on a bow which is aimed at Arcturus. The centre of the Milky Way galaxy and its supermassive black hole Sagittarius A star lie at the westernmost part of Sagittarius. Sagittarius A star is about 27,000 light-years away and has some 4.3 million times the mass of our Sun. It was in July back in 2016 that the solar system's barycenter moved outside the Sun, where it will remain until 2027. A barycenter is the gravitational centre of mass of a celestial system. For example, in our Earth-Moon system, the Earth and Moon actually orbit each other around a common centre of gravity, a barycenter. Now, because the Earth is so much more massive than the Moon, the barycenter is always inside the Earth's radius. If it were outside the Earth's radius, the Earth and Moon would instead have been classified as a binary planetary system, like Pluto and Charon. The solar system's centre of gravity or barycenter is usually located inside the Sun's radius. After all, the Sun contains over 99% of all the solar system's mass. But actually, the mass of the solar system is orbiting around the solar system's barycenter, which means the Sun also has a very slight spiralling 12-year orbit around the barycenter. And every now and then, when the planet's orbital positions are just right, especially when Jupiter and Saturn are nearest each other, their combined gravitational interactions move the solar system's barycenter ever so slightly outside the Sun's radius. And because Jupiter and Saturn reach this alignment every 11 years, some scientists have speculated whether this could trigger the Sun's 11-year solar cycle. And before you ask, the barycenter isn't named after some guy in a beige safari suit called Barry, but rather it's the ancient Greek word for heavy or centre of mass. We also have 2 meteor showers, both of which peak in late July. There's the southern delta Aquariids, which are visible from mid-July to mid-August each year, with peak activity on July the 28th and 29th. The shower originated either from the breakup of what are now the Marsden and Crack sun-grazing comets, or from the parent comet P96 Malkolts. The delta Aquariids get their name because their radiant appears to lie in the constellation Aquarius, near one of the constellation's brightest stars, Delta Aquarii. There are 2 branches to the Delta Aquariids meteor shower, the southern and northern. The southern Delta Aquariids are considered a strong shower, with an average of between 15 and 20 meteors an hour between midnight and dawn. Listeners in the southern hemisphere usually get the better show because the radiant is higher in the southern sky. Since the radiant is above the southern horizon for northern hemisphere listeners, meteors will be seen to fan out in all directions, east, north and west, with few meteors heading southwards, unless they're really short near the radiant. The northern Delta Aquariids are the weaker shower, peaking later in mid-August, with an average peak rate of about 10 meteors per hour. Meanwhile, the nearby slow and bright Alpha Capricornids meteor shower will take place from as early as July the 15th and continue until around August the 10th. The meteor shower has infrequent but relatively bright meteors and even some fireballs. It's generated as the Earth passes through a debris trail left by the comet 169P Neat, which was originally identified as the asteroid 2002 EX12. However, it was shown to be weakly active during perihelion and was then reclassified as a comet. The meteor shower was created about 3,500 to 5,000 years ago, when about half of the parent body disintegrated and fell into dust. The cloud eventually evolved into Earth's orbit, causing a shower with peak rates of about 5 meteors an hour and some outbursts of bright flaring comets, radiating out from the constellation Capricorn towards the south. The bulk of the comet's debris won't be in Earth's path until the 24th century, by which time the Alpha Capricornids are expected to become a major annual meteor storm, stronger than any current annual shower. Joining us now for the rest of our tour of the July night skies is Jonathan Alley, the editor of Australian Sky and Telescope magazine.
G'day, Stuart. Yeah, so it's July, more or less the middle of the year. It's middle of winter for us down here in the Southern Hemisphere, middle of summer for our friends up in the north, and I guess if you're in the middle of the planet, it's pretty much warm all year round. But it's certainly cold and dark down here at the moment where I live. But that's pretty good. Where I live, actually, even though it's cold and dark, the weather is actually pretty good normally during winter time. We don't get a lot of bad weather. That comes around when spring comes. The days can be really nice and clear, blue skies, and the nights can be really nice and clear as well. So you get nice dark skies, particularly if you're away from city lights and that kind of thing. So there's lots to see in the middle of the year, particularly for us down the south, because we're really lucky because we look into the direction of the middle of our galaxy, the Milky Way. Depending on your latitude, where you are in the world, you see different things. So for us, we are very lucky. Winter time, the middle of our galaxy is more or less directly overhead, and there's lots of great stuff you can see towards the middle of our galaxy because we're looking right in towards. If you imagine you're living in the outskirts of a city, if you look towards the city, you're going to see a lot of stuff between you and the middle of the city. But if you look in the other direction, further out into the outskirts, you're not going to see quite so much. That's basically how we are, where the solar system is placed. We're sort of on the outskirts a bit of the galaxy. But when we look in towards the middle of the galaxy, there's plenty of things to see. So the middle of the galaxy is around about the Sagittarius region, and next to that you've got Scorpius, or some people call it Scorpio. Lots of great stuff to see. Fantastic astronomical objects. You've got globular star clusters and open star clusters and dark nebulae and bright nebulae, interesting star patterns, all sorts of things. Sagittarius, for instance, has the famous Lagoon Nebula and the equally famous Trifid Nebula, which is my favourite nebula when I was growing up, probably also because it's the Trifid name. I saw the movie the other day, the Trifids, and that was scary as anything.
It's sort of stuck in your mind there, has it?
It's stick in the mind, but the Trifid Nebula is really beautiful, actually, and it's sort of this nebula is broken into 3 parts, and it's lovely and colourful. So lots of great stuff to see down there. Down in the southern part of our sky at the moment, we've got the Southern Cross. It's always down there. This time of year, it's nice and high. Sky means it's really nice and high, standing almost upright. Just to its left, you've got the stars we call the 2 pointers, which is the Alpha Centauri and Beta Centauri, which are very nearby stars. Around the area around the Southern Cross, actually, and over to its right is also within the Milky Way. To its right and to its left is also part of the Milky Way. And just like Sagittarius and Scorpius, you'll find lots and lots of great things to see around this area. Get a pair of binoculars and just have a squiz. You don't need a telescope, just binoculars are great. Just next to the Southern Cross, for instance, there's a big dark patch, like a big chunk that's been taken out of the Milky Way. This is actually a big cloud of interstellar dust and gas, and it's been nicknamed the coal sack for obvious reasons. It's been known by that name for a very long time. It really stands out if you have dark skies and you've let your eyes adapt to the dark after about 20 minutes or so. If you're in city lights, you might not see it quite so easily. Up in the northern half of our sky, at least, for us down here in the south, it seems pretty bare at this time of the year, but there are a couple of bright stars. You've got this one called Spica, which is the brightest star in the constellation Virgo. Everyone's heard of Virgo. There's another star called Arcturus, which is the brightest star in the constellation Boötes. Not a constellation most people are familiar with. It's spelled Bootes. That means the herdsman or the ploughman. That star, Arcturus, is actually the 4th brightest star in the night sky. And Spica, the other one I mentioned, is the 16th brightest. So they really stand out. Spanning across the northern half of the sky as we see it from the south, or southern half of the sky, or down towards the southern horizon as our friends in the north would see it, is part of the region that we call the zodiac, which is where all the zodiacal constellations are, your Tauruses and Geminis and all that sort of thing that people go on about. Virgo is one of them, is one of the constellations of the zodiac, and it's a very, very large constellation. And to the naked eye, it just seems really empty, nothing really bright about it in terms of stars and things. But astronomers love Virgo because if you've got a telescope and you have a look, you'll see lots and lots of galaxies. There's a famous galaxy cluster there called the Virgo cluster, and it's got lots and lots of galaxies. There's a brilliant galaxy in Virgo called M87. Now, Stuart, you would have mentioned M87 many times on the program over the years. This is the one that has that huge black hole in the centre that astronomers made that famous image of a couple of years ago.
And they're still finding new things out about it all the time, including its magnetic fields. This is the Event Horizon Telescope. And they're trying to do the same thing with Sagittarius A star. That's the black hole at the centre of the Milky Way. But it's proven to be a more difficult challenge.
Yeah, I think for 2 reasons. Perhaps one is that there's a lot of stuff between here and the centre of our galaxy that you've got to look through. And the other thing is that the black hole in the centre of our galaxy is much smaller than the one that's in M87. Even though M87 is a big galaxy that's a long way away, it's so big It's so huge. I mean, it is really giant. It's a gargantuan-sized galaxy, and the black hole in the middle of it is equally gargantuan. Yeah, so that one's in Virgo. There's another one in Virgo I really love. I've always loved this one again since I was a kid. It's this big spiral galaxy, very distinct dust lane running right around the middle, and it's really symmetrical. And because of its appearance, it's been nicknamed the Sombrero Galaxy. If you have a look at a picture of the Sombrero Galaxy on the internet these days, you'll think, well,
it's one of my favourite-looking galaxies.
It's a beautiful galaxy.
You might not see the dust lanes. You get to see. You can almost see it in 3 dimensions. The way we're looking at it, almost edge on, but because of the way we're looking at it, there's lots of light and shadow there. You get to see the dust lanes.
If it was exactly edge on, it wouldn't look quite as good. It's because it's a little bit angled on. It looks really 3D, as you say.
And you can see the little lumps and bumps in the structure of the whole thing. It is spectacular, and you realise that is full of planets just like us.
Yeah, it's amazing. It's an amazing galaxy. If you have a look at a really good picture of it, you probably won't see a sombrero in it, but you won't think, oh, how they get a sombrero out of that? It's because in the old days when people were just looking through telescopes with their eyes, or with the old style photography, which wasn't that crash hot compared to the fantastic electronic cameras we have today, what you saw back then was mainly the top half of the galaxy with this dark rim going around it, and that made it look like a sombrero hat. The better cameras you've got these days also shows the bottom half nice and bright, so it looks more like what does it look like? It looks like a UFO, I suppose. But let's not get into that.
No, let's
not go into that one. But actually, it's a really good. So anyway, lots and lots of stuff to see in the constellation Virgo. So let's now take a look at the planets, see what's happening there. Well, we'll start looking to the west just after the sun has set, the beginning of July. Down near the horizon, you'll see what looks to be a big, bright star. Well, that's not a star, that's actually the planet Venus, and you can't miss it because it's really big and bright. And not far above Venus, you'll see a dimmer reddish-coloured star. Well, that's also not a star, that's the planet Mars. Okay, so you've got Venus and Mars quite close together over there in the western sky, not far above the horizon after the sun's gone down. Now, keep an eye on these two planets as July begins, and you'll see that Venus is rising higher and higher in the sky as each day goes past and getting closer and closer to Mars. And from the 12th to the 15th of July, they'll be really close together. They'll only be 1 degree or less of an angle separating them, so they'll appear to be more or less side by side. The moon, when we look at the moon's about half a degree across, so these two will be separated by about 2 moon diameters, which is pretty close as things go in the sky. Of course, they're not actually really close to each other out there in space, just they happen to be in the same line of sight. That's what we talk about when we say they're close in the sky. They're in the same sort of line of sight. Speaking of the moon, if you go out on the 12th and have a look, the moon is going to be right next to them as well, so that should be a pretty specky sight. You'll have Mars, Venus, and the moon all lined up. Now, as the month goes on, Mars will remain roughly in the same spot as it is. It's going to slowly get lower and lower in the sky, but not too much as the days go past. But Venus will continue to climb higher and higher above the horizon. Now, the innermost planet, Mercury, is always pretty hard to spot, actually. It doesn't really rise very high above the horizon normally. So if you have any trees or hills or buildings or anything in the way, chances are the planet is most of the time out of view for you. But this month, you're going to have to be an early riser. You have to be up before dawn, as Mercury will be above the eastern horizon before the sun comes up, but only for the first couple of weeks. And it's going to be pretty low down, even at its highest point, only about 7 or 8 degrees above the horizon. And as the weeks go by, it'll be dropping lower and lower towards the horizon, and then it'll get lost in the glare of the sun as the sun starts to come up. Now, the other 2 big planets, or the 2 biggest planets in the solar system, Saturn and Jupiter, well, they're what we call evening objects. At the moment, we can see them in the evening. They're rising above the eastern horizon not too long after the sun's gone down, and therefore they're visible for pretty much all of the night. Saturn's rising around about 7:30 p.m. at the start of the month for stargazers that are at the latitude of Sydney in Australia. If you're at the latitude of New York in North America, it'll be different for you because it's summertime up there or it's wintertime down here. So Saturn's rising about 7:30 p.m. start of July for people mid-latitudes in the southern hemisphere. By the end of the month, it'll be about 2 hours earlier than that, so it'll actually be already over the horizon as the sun goes down, as the sky starts to get dark. That's Saturn, and Jupiter follows it up above the horizon about an hour and a half later, so they're not too far apart in the sky. Saturn comes up first, and then Jupiter follows about an hour and a half later. Next month, both of these planets are going to reach what astronomers call opposition, and this is when a planet and the sun are directly on opposite sides of the Earth, so One direction there, you've got the sun, and the other direction, 180 degrees opposite, is the planet. This means that for us standing on the surface of the Earth, as the sun's going down in the west, planets rising above the horizon over there in the east. The practical upshot of that is that if you like to do stargazing, it means that the planet's going to be up all night. From the moment of sunset all the way through till dawn, it's going to be visible, weather permitting. Opposition's also more or less the same time as when a planet is closest to the Earth. Even though that's a very long way away for both Jupiter and Saturn, they'll still be closest to the Earth, and therefore being closer, they'll appear a bit bigger than they normally do. And that means if you have a look through a telescope, you'll be able to make out more detail than you normally would. So, next month, August, it should be really, really good. Astronomers are going to look forward to that. Both of these giant planets coming to opposition in the same month.
That's Jonathan Alley, the editor of Australian Sky and Telescope magazine. And don't forget, if you're having trouble getting your copy of Australian Sky and Telescope magazine from your usual retailer because of the current lockdown and travel restrictions, you can always get a print or digital subscription and have the magazine delivered directly to your letterbox or inbox. Subscribing's easy. Just go to skyandtelescope.com.au. That's skyandtelescope.com.au, and you'll never be left in the dark again. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.